Everyone, welcome to our final day of talks. As always, we will have 2 talks and then save the questions to a question and answer session after the 2 talks. The first talk will be by Yan Qi from Fudan University.
Okay, I would like to first thank the organizers for putting up this nice program and thank them for giving me the chance to talk about our recent progress here. So due to the time I have, I think, and also due to the fact that I haven't been able to talk to most of the people here due to the current circumstances, I think I will just give a short brief view of what we have been doing towards the classification of fermionic crystalline SPT phases. I will omit most of the details and just give a brief introduction. And if you are interested in the details, we can talk about that later, maybe afterwards. So let me first thank my collaborators. So I will primarily talk about 2 works. The first one is done with Zhida Song, who was a student of Professor Chen Fang when we were doing this work, but he's now, actually he's coming back to China, to Beijing University to join their faculty, and also with Professor Chen Fang from IOP in Beijing. And the second work is done with my student, Ouyang Yunqing, and also Dr. Qingrui Wang, who is actually coming back to Tsinghua University to join the faculty at the Yao Center of Mathematics, I think. And here are the two references if you are interested in. So here's my outline. I will first give a very brief 1-page introduction to SPT phases, and then I will talk about the 2 approaches we're trying to solve the problem. The first one is to use the crystalline equivalence principle, and the second one is to do the real space construction. I will briefly explain what they mean later, and then I will conclude. So first, let me give a very brief introduction to what are the symmetry protected topological phases. I think most of you know this concept very well. So they are gap topological phases beyond Landau paradigm of classifying phases using symmetry breaking. And in the bulk, a non-trivial SPT phase in the bulk is gapped and has no fractional excitations, but they cannot be smoothly connected or smoothly tuned to a trivial phase without going through a phase transition or symmetry breaking. And on the surface, you will have some symmetry anomaly, which is usually reflected in some symmetry protected gapless surface states or some anomalous SET phases in higher dimensions. And there are 3 types of SPT phases mostly. The first type is the simplest type is free fermion SPT phases, which here the famous examples include topological insulators, topological superconductors, and these are well understood using the K theory in mathematics. And the second type is bosonic SPT phases, and the famous examples of that include 1-dimensional Haugen chains, and also in 2 dimensions we have the CZX or the Levin-Gould states. And the classification of those states are also quite well understood. They are mostly classified by the group cohomology theory. And the third and the most difficult type is the interacting fermionic SPT phases. And to my knowledge, I think that this classification problem is not fully solved yet. So that will be my topic. And also I will focus on the SPT phases protected by space group symmetries and maybe some other on-site symmetries. And people also call this crystalline SPT phases because space group symmetries are the symmetry groups for crystals. I think here we have 2 approaches to approach this problem. The first is to use the crystalline equivalence principle introduced by Ryan Thungren and Dominic Els. I will talk about that in details later. And the second approach is to use real space construction, which started from the concept or the method of dimensional reduction pioneered by Liang Fu and Michael Hermle et al. And the famous examples include, like, if you have a mirror symmetry, you can put some on-site symmetry protected SPT faces on the mirror plane, and then you get a mirror SPT. Or you can stack some two-dimensional SPT faces in a periodic manner, and you get a weak SPT face protected by translation symmetries. But later on, people figure out that we can generalize it to quite arbitrary space group symmetries. So I will first talk about the approach using crystalline equivalence principle. This principle, due to Thorngren and else, tells us that basically we can treat the crystalline symmetries just as on-site symmetries, and the computation will give you the same classification results. So the rules are, first you treat the crystalline symmetry group as an on-site symmetry group with the same algebraic structure. For example, if you have an on-site Z2 symmetry like Ising Z2 symmetry, the classification protected by this Ising symmetry is the same as the SPT faces protected by C2 rotation symmetry. And the second rule is that if the space group symmetry reverses space orientations like a mirror symmetry or glide plane symmetry, you should treat that as anti-unitary symmetries. A third rule is that for fermions, you have you could either have spinless or spin one-half fermions, and the correspondence is twisted. So if you have, for example, the classification of C2 symmetric fermionic SPT faces, if the fermion has C2 square equals to +1 or -1, that corresponds to an on-site symmetry with which squares to -1 or +1 respectively. So the +1 goes to -1, -1 goes to +1. So in this way, we actually the problem of computing the classifications is the same for crystalline and on-site symmetries. And the problem becomes that we need to compute the classification for crystalline symmetry groups, just treating them as on-site symmetries. But the difficulty is that the crystalline symmetries are usually quite complicated symmetry groups, like they have an infinite number of elements. So here we have a technical problem that we need an efficient algorithm to deal with such large symmetry groups. The thing we have done is we developed an efficient algorithm to deal with such complex symmetry groups. I will give a brief idea of what we are doing. So let me give a very brief introduction to the group cohomology theory that classifies the bosonic SPT faces. I will focus on the computational point of view instead of the mathematical one. So the bosonic SPT faces are classified by the group cohomologies. So in one line, that's the cohomology is actually dealing with the Cauchy functions, which can be viewed as some vector in a linear space. So here, the linear space goes with quote unquote because it's mathematically it's not a linear space with coefficients in a field, but it's rather a module with integer coefficients. But I will ignore that difference. I just call it linear space and linear math. You can view these as linear functions or vectors with basis that's generated by the combination of group elements here. So you can imagine that the dimension of the linear space goes to the order of group to the power of n. Here, the technical details that you can subtract 1, but basically to estimate the computational cost for large symmetry groups, you can basically ignore this. Sorry about that. So this algorithm is very expensive if the symmetry group has many elements. And in particular, for space groups that contain infinite number of elements, this algorithm is not going to work. So the solution to this is actually we can change the basis and use a much smaller basis, which mathematically is known that you can use a much smaller basis that generates the same cohomology groups. So to give you some ideas, so the mathematical construction behind this is that the basis we're using is actually some cells of a classifying space. And the classifying space have some standard construction, but you can have a smarter, simpler construction that contains much less cells, and this will give you a much smaller linear space that will allow a more efficient calculation. For example, for the CN or DN group, if we use the standard construction, the dimensionality grows quite rapidly. But if we use a reduced construction, then the dimension goes much slower. We can also generalize this to fermionic SPT phases. I think I'm running out of time, so I will skip. I have to skip some details. So for fermionic SPT phases, actually the most difficult part is to compute some abstraction functions that essentially is some linear maps between two linear spaces. So using the basis, so the idea is that we can construct a basis transformation that mathematically is known as a chain map that maps between the reduced and the standard construction of linear spaces, and this will reduce the computational cost. So we have developed a computer package in GAP that allows us to compute the fermionic SPT phases for all the 2D wallpaper symmetry groups. So we're actually developing this software package. So if you are interested in using it, or if you have some similar tasks that could use our package, you're welcome to contact us for the early access to this package. I think maybe I have a few minutes to summarize our second approach. So the second approach is that we try to break the whole space into smaller pieces, like smaller cells. And we do it in a way that on each cell, we only have on-site symmetry. So for example, if here's a cell with a C2 symmetry, we cut it in two parts such that each part have no symmetry, crystalline symmetry at all if we consider only one of them, and only the central point has a C2 symmetry, which acts as an on-site symmetry. And after we do this decomposition, we can put on-site symmetry protected SPT phases on each pieces. And then we can use some consistency conditions to figure out whether we can glue them together without leaving any symmetry protected edge states on the interfaces. And also we need to model out some equivalence classes, because there are some equivalence process that we can use to deform a decoration to another one without closing the gap or breaking the symmetry. So by definition, this should be considered as the same topological states. For example, if you create a bubble of SPT faces inside a three-dimensional cell and enlarge it such that it fills the entire cell, that would put some additional SPT faces on each side of the on each side of this cube. But this process does not close the gap or break symmetries. So the whole process keeps the SPT classification. So that means two decorations can belong to the same SPT face. We need to model that equivalence. And we need to do this step by step. For example, we can start with some 2D decorations and then fill out the one-dimensional interfaces. And after that, we need to fill out the zero-dimensional interfaces between the one-dimensional interfaces. And it turns out this calculation can be organized as a spectral sequence, which is a mathematical tool people use to compute cohomology groups. So for people who are interested in the mathematical details, the spectral sequence we are using can be found in this famous book of cohomology of groups. And mathematically, we can prove that for bosonic SPT phases, this works and can give a complete classification of bosonic SPT phases. And we have been trying to generalize this to fermionic SPT phases. And basically here, we can compute the fermionic SPT phases protected by the 2D wallpaper groups using the two approaches. One is a real space construction, and one is treat the symmetry group as an on-site symmetry group. And the two approaches do agree if we take into account the twist between spin-1 half and spinless fermions. So let me list some related works. For the second part, there's an independent work by Els and Thangri. And also, I would like to mention that for the first part, the same algorithm was also used by mathematicians to compute some cohomology groups of two groups. And to summarize, I think what we know here, the progress is that we know how to compute on-site symmetry classifications for 1D and 2D fermionic SPT phases, but there are some corner cases for 3D classifications that we still don't know. So because of that, we can't use the on-site symmetry classification results for crystalline symmetry SPTs in 3D. So people have to solve that problem first. And also for fermionic SPT phases, if we do a real space construction, we have only done this case by case, so we don't know exactly what's the general rule, and we don't have an automated program to do that. That also needs to be done in the future. I think I'm basically out of time, so that'll be it. And thank you for your attention.
Okay, yeah, thank you very much, Jan, for that nice talk and for finishing on time.
End the screen share, right?
Yeah, well, I think
it's already
even if you want to just share your